do the math work. Yeah. All right. So with this modeling function, complex trigonometric polynomial, this modeling function. Now, let's go back to our data, discrete, yeah. The sampling values, the data points. Yeah. All right. And this function, the modeling function, should pass through all the data points, right? Yeah. Or in other words, you can say all the data points must be on this function. Yeah. So if you plug in, you have that, x, y coordinates on the curve of this function. Yeah. Yeah. So that assumption, okay? So that basic assumption. Yeah. With that, so we should have the formula representation. Yeah. That property should be represented at the beginning. Yeah. All right. So we call it interpolation. So this function interpolates all the data points. That assumption. Okay? So our first assumption is this interpolation assumption. Yeah. That is, so we plug in the values. Yeah. So the function value, remember that f is some imaginary function, right? Yeah. Because you never see the real f function. You can never see that real f function. You can only imagine that f function. Now you use this q function. Definitely this q function is different from some hidden, so you imaginary hidden f function, different. But the q function and f function has the relationship is these two functions have the same function values at these sampling points. Yeah. All the x locations, these two functions are the same, have the same values. That's the property, interpolation property. Okay, all right. Yeah. So the q functions, yeah, you have that. Yeah, all right. Yeah, because we never know the original f function. So the best thing we can do, we use some nice, convenient q function. That's the complex trigonometric polynomial to model the original function. Yeah. And we'll hope the result is good enough. That's our hope when we solve real-world problems. Yeah. All right. Then, now we need to determine this q function. We haven't determined the q function. Okay? Yeah. So when we use this q function, the modeling function, all the coefficients, c coefficients, are undetermined. We need to find the c coefficient values. It's unknown. All the c coefficients are unknown. So we need to solve a linear system to find these c coefficients. So our next step, we need to determine the c coefficients. All right. How to determine the c coefficients? Yeah. Here we can see it's a linear system, right? Yeah. By solving a linear system, we can get the c coefficients. Yeah. So let's do it. Yeah. Formulas for the discrete Fourier coefficients. Yeah. So those c coefficients we called discrete Fourier coefficients. Yeah. All right. Let's make that linear system. Yeah. Let's write out. Yeah. So what's that linear system? Yeah. All right. Yeah. Yeah. All right. So here you can see this is the formula. The Cn formula can be represented in this way. Yeah. So you may ask, how can you see it? Right? Yeah. How can you see it? Yeah. So there are several ways you can see it. Yeah. Cn function. Yeah. So think about it. To see the Cn representation, we may like to go back to our continuous case. In our continuous Fourier transform, we get a coefficient, B coefficient, An, right? Bn. Yeah, remember? We have An formula and we have Bn formula. Yeah. Two sets of coefficients. Yeah. But here, because here we use the complex basis functions, so we only need one set of coefficients, Cn. Yeah. So that is another nice thing about the complex functions. When you use complex functions, you only need one set of coefficients, Cn. Yeah. Yeah. In that continuous version, sine, cosine, we need two sets of coefficients, A and Bn. Yeah. Yeah. Here, to determine the Cn coefficients, we can use the similar way that we used in our continuous version. Yeah. So here, we need to recall, how do we get the A and Bn coefficients in the continuous Fourier transform? Yeah. Remember, we based on the orthogonality property of the basis functions. Yeah. So how do we get these coefficients? By the orthogonality. That property. Okay? Yeah. Yeah. The good thing is, for our E basis function, these E basis functions, we also have the similar orthogonality property. Okay? These E basis functions. Yeah. So E basis functions. Okay? So what are the E basis functions? Because the E basis functions start from 1. Yeah. Yeah. Because when n equals 0, so it's 1. Then e to the ix, e to the 2ix, and so on. Okay? Yeah. The last one, e to the m minus 1 ix. Yeah. So these basis functions. Yeah. Then there is an important property we need to use, the similar orthogonality. Yeah. Or we can call the generalization of the orthogonality. Generalized orthogonality property. Okay? Yeah. So the continuous version, that integral, 0, 1, orthogonality property, right? Yeah. So here, this set of basis function, there is a generalized orthogonality property. Orthogonality. Yeah. Similar. Okay? Yeah. So now the integral in the summation. Okay? Yeah. In that 1/n times that summation. That kind of operation. This operation, because we know summation, this is a discrete version of the integral. Yeah. Integral we know that operation, let's say pi to pi, integral, we know that's a continuous version of the summation. Yeah. So if you recall the area, right? Yeah. So what's the meaning of the integral? The geometric meaning of integral, the area under the curve. Yeah. And how to calculate area? So you make a lot of slices. Yeah. Slices. So each slice you use a rectangle to represent each slice, to approximate. Then you take summation of all the areas of those rectangles. Yeah. You take summation, so you get an integral. Yeah. That's the definition of the integral. Yeah. Now, because here you need to do the discretization. Yeah. Discretization. Yeah. When you do that, you use the summation to represent the integral. Okay? Yeah. Okay. Yeah. Go ahead. Yeah. All right. And in this summation version, we have the similar orthogonality property. Okay? Yeah. All right. So that the Cn coefficients can be represented by that generalized orthogonality property. Yeah. So we can easily get that. So that's one way to find these C coefficients. All right. Yeah. So discrete, yeah. So after you calculate these Cn coefficients, yeah, then our discrete Fourier transform we can define. Yeah. Not the definition. Yeah, define. Yeah. Then remember the transformation side, the frequency side. So this is the frequency side. The frequency side, yeah, we should have a sequence of numbers. Yeah. So the sequence of numbers, this f hat n, sequence of numbers. So each number we represent it as a summation. Yeah. That's the Fourier transform. That's the discrete Fourier. That's the definition of the discrete Fourier transform. Okay? Yeah. Fn. Yeah. So here you can see, yeah. What do we do in the time domain? We have a sequence of sampling values. Then we apply discrete Fourier transform. We move to the frequency domain, so we get a sequence of frequency sampling values. Yeah, also sampling values. Frequency. Yeah. Same number. Okay? Yeah. Same number. Yeah. In a time domain, you have capital N samples. Then when you transform to the frequency domain, you have the same number of samples, also N, capital N. Okay? Yeah. So that's the definition of discrete Fourier transform. Yeah. All right. Then, given a signal, we use F vector. Yeah. So now we want to use the matrix representation. Yeah. 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 But here, because here the summation, if we use the matrix representation, yeah, so we can have some relatively simpler representation. Yeah. So the original signal, we can put it in a one vector. Yeah. Yeah. This n-dimensional vector. Yeah. Yeah. All right. Here this T means transpose. Yeah. Transpose. So the vector should be a column vector. Yeah. But here we write it as a row vector to save some space. Yeah. The reason people write it as a row vector because we can save some space. Okay? Yeah. Then we put a transpose notation. Yeah. So the vector should be a column vector. Yeah. All right. Then when we do the discrete Fourier transform, we get another vector, F vector, that hat version. So it is another vector, same dimension, yeah, and the values we can use the definition of this discrete Fourier transform formula. We can calculate. Yep. All right. All right. Yeah. Yeah. So this way people call it frequency spectrum. Yeah. Frequency spectrum. Yeah. So you collect your signal content from all the frequencies put together, so you have that frequency spectrum. That concept. Okay? All right. Yeah. Notations. Yeah. Now, with this vector representation of the signal, then the coefficient part, we can use a matrix to store the C coefficients, and all the coefficients we need to use to do the discrete Fourier transform and inverse discrete Fourier transform. Yeah. Because when we talk about Fourier transform, at the same time we need to look at the inverse discrete Fourier transform. All right. Yeah. Yeah. So here we introduce a W notation to represent this, E. Yeah. E to the negative 2 pi I over M. Because all other E terms, we can use this W notation, certain power of this W notation to represent. Yeah. So here we use this little W. Yeah. Then discrete Fourier transform, we can use a, matrix multiplication. Yeah. So we can find appropriate capital F matrix, capital N by N matrix, square matrix, to this multiplication. So what is this capital Fn matrix? Using the little w entry. The entry, the exponent number n times k. Yeah. And taking from 0 to capital N minus 1, k taking from 0 to capital N minus 1. Yeah. So here you can see it's an n by n matrix. Yeah. Yeah. So if you compare, if you multiply matrix vector out, you can see exactly that's our discrete Fourier transform. Then the notation becomes very simple. Yeah. Matrix multiplication. Yeah. Straightforward. Yeah. All right, the short notation. Yeah. All right. Next. Yeah. So this matrix we call the Fourier matrix. Yeah. Next, we need to consider the inverse Fourier transform, right? Yeah. So the discrete Fourier transform, as simple as that. Yeah. But what is the inverse discrete Fourier transform? Yeah. Yeah. We don't want to see a very complicated inverse Fourier transform. Okay? Yeah. Very complicated one. Yeah. Yeah. So let's see. Can we have a very simple representation for the inverse Fourier transform? Yeah. Let's continue to see it. For the inverse discrete Fourier transform, yeah. Then you take matrix inverse, right? Yeah. So if we from the first, from this equation, we can take a matrix inverse. So that n by n matrix, we hope it's invertible. Later we can prove it's invertible. So if we go directly from the formula, the inverse transform, we just take the matrix inverse. We know there is a formula to calculate the matrix inverse. All right. But the question is, if you apply the formula to calculate matrix n by n matrix inverse, very complicated. Although the formula exists, okay? You plug in numbers, you can calculate matrix inverse. But if you really do it in that way, you need to spend a lot of time. Very time consuming. Matrix inverse calculation is very time consuming. Okay? Time consuming. Calculation. So, too slow. So we like to have a faster and easier way to find its inverse. So the first thing is there much simpler way to find the inverse without time-consuming calculation? That's the next question. Okay? The answer is yes. There is a very simple way to find its inverse. Because this matrix, this Fourier matrix, is a very special matrix. Especially, remember that orthogonality I mentioned before, that generalized orthogonality I mentioned before. This generalized property, orthogonality property, we can use it to find its inverse easily. That's the reason, we can write it, its inverse representation quickly, easily. Okay? All right. So let's look at how to write it out. Here. All right. Complex conjugate of z. When we do that, we need to recall some old notations. For a general representation of a complex number, we use a plus bi. A the real part, b the complex part. Okay, so a plus bi. So it's a general representation of the z complex number. There, for the complex number, there is a very important operation, the complex conjugate operation. That is, we use the notation z bar. So that bar represents conjugate of that z. The conjugate is defined as a minus bi. You only change the sign of the imaginary part. Imaginary. Real part, the same real part. But imaginary part, you change the sign. So if you want to ask why you define this complex conjugate, because there is a nice property. If you define in this way, there is a nice property. If z, look at z times z bar. What's that? You do the product, z times z bar, a plus bi times a minus bi. By the formula, a squared minus b squared and I squared, right? We know I squared equals negative 1. So you replace I squared by negative 1. So a squared minus b square I square, it becomes a square plus b square. Okay? Yeah. Sum of squares of the real part and the imaginary part. See? So that's something very nice. The product. Yeah, so that's the reason people define this complex conjugate concept. Yeah, very useful. Yeah, complex conjugate concept. Yeah. All right. So with this definition, yeah, then let's look at a W bar. Yeah, yeah. W bar, because the original W, there is a negative sign in front of 2 pi I over capital N. So its conjugate version, yeah, so we change that negative sign to positive sign. Yeah. That's the bar thing. Yeah, because if you use the Euler formula, sine, cosine, right? The cosine part negative, yeah, so you change the sign, you make the cosine, you make the sine part negative. Yeah. The cosine part negative, no change, right? Yeah. So you can see that easily. Yeah. The conjugate. Yeah. Then the Fourier matrix, now you look at the bar, the conjugate of the Fourier matrix. Yeah. What's that conjugate? The conjugate for each entry, each matrix entry, you take conjugate. Complex, yeah, so the full name we call a complex conjugate. Yeah. Because for other structure there are different conjugates. Yeah. So other different structure we can define different types of conjugates. Here, this is our complex conjugate definition. Yeah. All right. So you have the conjugate matrix of the Fourier matrix. Yeah. Very simple, right? You can write it out easily. Yeah. All right. Then the key property, yeah. Then there is an important property for this Fourier matrix. Yeah. So this property helps us to find the inverse matrix of the Fourier matrix easily. So what's that property? That is, if you do matrix multiplication, the complex conjugate times the Fourier matrix, yeah, bar conjugate, yeah, equals n times identity matrix. Yeah. Now you can see the inverse matrix is pretty much there, right? Yeah, because this identity very close to the identity we use for the inverse matrix. Yeah. Yeah. So the inverse Fourier transform, that inverse matrix is 1 over n times the complex conjugate of the Fourier matrix. That's simple. Yeah. Because in this way, when you use this matrix, you don't need to do the inverse matrix calculation, right? Yeah. We know inverse matrix calculation, very time consuming. Yeah. We don't want to calculate directly. Yeah. But we have nice properties here. Yeah. Based on this nice property, yeah, so we can write out the inverse matrix easily. Yeah. All right. Yeah. So here a simple example. Yeah. Yeah. Given a signal with 4 sampling values. Yeah. The dimension vector, these 4 numbers. That's our signal. Yeah. All right. Then, because we need to write out the little w, yeah. So based on the structure of the Fourier matrix, so we write it out. Yeah. Then you do matrix multiplication, so you get a discrete Fourier transform like that. Okay? So when you do calculation, yeah, that's the discrete Fourier transform. Yeah. So you go to the frequency domain. Yeah. So with these values, now you work in the frequency domain. Yeah. Frequency domain, so we can apply various operations in the frequency domain, yeah, to do processing. Yeah. After that, then we go back to the time domain. Okay? Yeah. Yeah. By inverse Fourier transform, we go back to the time domain. Yeah. All right. Yeah. Yeah. So here you can see. Yeah. So before we finish this topic, here you can see. Later, when we do Fourier transform, Fourier inverse transform, we just do the matrix multiplication like this. Yeah. Yeah. All right. Yeah. Then consider in the real world situation, yeah, you need to do matrix multiplication like this. But we know matrix multiplication, you need to do a lot of multiplication, a lot of scalar multiplication, right? Yeah. So the rows, columns, each row, then the column vector, you do multiplication. So there are large number of multiplications you need to calculate. Yeah. Although you use computer software to do the calculation. But it takes time, right? Yeah. Especially when your data size is large. Yeah. So the matrix multiplication takes a lot of time. Yeah. So the next question is, how to make this matrix multiplication much faster. Yeah. Yeah. The next question we need to answer: how to make this multiplication much faster? Okay? Yeah. Yeah. So that's the topic, Yeah. Next class topic I want to talk about the fast Fourier transform. Fast, okay? Yeah. So it's a very useful method, algorithm in real world application. It's called fast Fourier transform. Yeah. So next part, next class, I want to talk about this fast Fourier transform. Yeah. Because in your real world application, you need to use software. Yeah. You need to apply fast Fourier transform many, many times. Yeah. But you use software. Okay? And the improvement is big. Yeah. So next time I will talk about how much improvement we can get by the fast Fourier transform. So what's the idea? The method. Yeah. All right. Yeah. Then next, I'll give you a few examples. Yeah. So because for this part, the Fourier transform, we haven't seen examples. So I like to give you a few examples. Yeah. All right. For example, we solve ODE by Fourier series. Yeah. Yeah. Here the method we used quite similar to the power series method. Yeah. So let's recall the power series method. How do we apply the power series to find ODE solution. Yeah. So here, the main difference is we replace the power series by Fourier series. That's the only difference. Then the general process pretty much the same. Yeah. Yeah. Just the formula details different. Yeah. The idea, the process, almost the same. Here, let me show you a simple example. Yeah. Find a particular solution of the ODE. Yeah. So the second order ODE, but the R function, this time the R function. R function, here you can see it's a periodic function. Yeah. So periodic function, then it's better we use Fourier series. Okay? Periodic function. It's better than the power series, right? Yeah. Yeah. Because the structure, the Fourier series is a better representation for a periodic function than the power series. Yeah. All right? Yeah. So here, yeah. All right. 2 pi periodic. Okay? All right. So here, let us calculate the Fourier series first. Yeah. Yeah. When we do the calculation, first we can see this R function is an even function, right? Yeah. Even function, then we know that all the B coefficients are 0. All the sine terms are gone. So we don't need to calculate the sine part. Yeah, all 0. So we only need to calculate the coefficients for the cosine functions. Yeah. So the representation is like this. Yeah. A0, yeah. So we calculate the A0 easily. Yeah. All right. So by, just some simple calculation, we can get the A0, 1/2. Yeah. Then all the other A coefficients, yeah. So we apply the formula here. Okay. Yeah. Yeah. All right. Then, yeah, on different interval, yeah, because the absolute value for different interval, yeah, the sign different. Yeah. So we do the calculation. Yeah. So you can see the answer. Yeah. Answer for even number and odd number. Yeah. Representation is different. Yeah. So here we want to see for even function, odd function, what's that? Yeah. All right. Then for when n is odd function, we can find all the coefficients are 0. Odd function. Yeah. All right. Then for even function, we do the calculation, simplification. Yeah. The simplification like that. Okay. Yeah. Then we can write Fourier series of R functions in this way. Yeah. So the first step, we need to write its Fourier series representation for the R function. Okay. So you just do the calculation carefully, yeah, for each coefficient. Yeah. After that, then we calculate our solution, particular solution. Yeah. We only need to calculate one particular solution. Yeah. All right. To calculate the particular solution, then you can see the R function is sum of a sequence of cosine functions. Yeah. All right. So let's do term by term. So here we use the idea. Yeah. We use the linearity property. Yeah. Because when we solve this ODE, this linear ODE, we can apply the linearity property. Yeah. That means we only need to consider when R equals the first term, there is a solution, right? the R for the second term solution, third term solution, and so on. Then, for all those components of the solution, we add them up. We get a whole solution. Because we can do that by the linear radius property. Okay? Yeah. All right. So form of the solution, we represent it as the sum of y0, y2, y4. y0 corresponds to the first term. y2 corresponds term with cosine 2t and so on. Okay? Yeah. Then we calculate each y function separately. Yeah. So let's calculate. Yeah. So the general case, yeah, an like that. Yeah. Yeah. Or 2k. Yeah. Yeah. 2k like that. Yeah. All right. But y0, let's take it out. Let's assume y0 function, it's a constant. Yeah. The constant part. Yeah. Let's plug in. So when the y0 function is a constant, let's plug it into the original function. Yeah. Because double derivative on a constant, it's 0. So we only have omega squared times y0, it's capital C, equals 1/2, equals the first term of the R function, 1/2. Okay? Yeah. So we can find the capital C equals 1/2 omega squared. So that's for the first y component. Yeah. Then, second, the remaining y components, yeah, because we can work on this equation. Okay? Yeah. How to solve that equation? Yeah. So in our module 2, yeah, we know, yeah, we can use, remember the choice rules, right? Yeah. We apply the choice rules to determine that y2k. Yeah. So by the choice rules, y2k should take this form. Yeah. We need to determine capital A sub 2k, capital B sub 2k coefficients. Yeah. Undetermined coefficients. Choice rule. Okay. The first choice rule, there are 3. Okay. 3 rules. We do the first one. All right. Then you plug in. You take double derivatives. You have that. Yeah. Omega. That. Yeah. So here the calculation. You need to be very patient to do the calculation. Yeah. Here we do calculation carefully. Yeah. All right. So there, yeah, because we compare, after we derive this equation, we compare the cosine part and the sine part. Sine part, the right-hand side, no sine part, right? 0. So that's why all the B coefficient becomes 0. The cosine part, then we can find the capital A sub 2k, the cosine part. Yeah. All right. Then we can write the final particular solution in this way. Yeah. So we find the particular solution by the Fourier series. Yeah. So that's the standard way. Yeah. Although the calculation, you need to spend a lot of time doing the calculation. Yeah. So in this homework assignment I just gave you yesterday, yeah, homework assignment 4B, question number 9, similar question like this one. Okay, yeah, you just use this example to help you solve question number 9 in the homework assignment 4B. Yeah, yeah, based on this example. Okay, yeah, yeah, yeah. All right, yeah, yeah. It should not be very hard if you calculate carefully. Yeah, it is not very hard. Yeah, yeah, yeah. You need to do quite some work. Yeah. quite some work. Yeah, similar to the work in this example. Yeah, Fourier series. After that, components. Each one, you need to find expression. Then you add them up. Yeah. All right. So that's this example. Yeah. The last one is apply Parseval's identity. We have another similar question in the homework assignment. Yeah. So I give you. Yeah. It is very simple. Yeah. But let me leave it next time. Yeah. Because the example is pretty straightforward. Yeah. The example relatively easy and straightforward. Yeah. So next time I can use 5 minutes. I can complete this example. Yeah. So that's for one of the homework questions. Yeah. The homework actually I give you 2 questions regarding this topic. I give you 2 questions, 2 consecutive questions. The first question, you need to find the Fourier series. Yeah. The second question, the second part, you apply the Parseval's identity. You prove some identity. Okay. Yeah. So 2 questions. For this topic. Yeah. 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 It should be quite easy. Yeah. Quite easy. All right. So let's stop.